So in the last video, we talked about value iteration as one algorithm to actually solve an MDP. We directly worked on the value function, so we actually calculated the optimal value function directly on the state space, which is fine, but there's also another way to do this, and this is policy iteration, and this is what we will do in this video. So instead of in value iteration, what we did is we directly worked on the value function, and the policy was just extracted at the end. So actually, when we had our value function calculated, we extracted a policy that was just being meant to be the greedy policy over the state over the value function. In this case, in this video, we will introduce policy iteration, and policy iteration maintains an explicit representation of the policy throughout the iterations of the algorithm. So that's the main difference between value iteration and policy iteration. And we can also formalize this a little bit in a single picture. So the idea of, while value iteration directly works on the state space, we have an alternating procedure in policy iteration, and the alternating procedure is something that we will also build upon in the next lecture. This is why we generalize it a little bit. And what you see on this slide is the generalized policy iteration method, which basically says that we have some initial, given a known MDP, we start with an initial estimate of a value function and an initial policy. So the initial estimate of the value function could just be a zero initialized value function, and an initial policy could just be a random policy. And the basic procedure behind GPI, or generalized policy iteration, is that we, based on the policy, we want to estimate the value function. So we want to estimate, instead of V star, which is something that we did with value iteration, we want to estimate V pi. So we want to know the state value function in the MDP if we follow a policy pi. Given this value function, we want to update our policy, which basically means that we want to update the policy and want to act greedy to our current value function estimate. With this updated policy, you will see the intuition a little bit through examples in the upcoming slides. We will again estimate our value function, because actually the policy changes. We actually updated our policy because we're now being greedy with respect to a value function which has changed. We need to update our value function. Based on this value function, we will update our policy. And if we keep iterating on that, we will finally end up in the optimal policy and optimal value function. So we will always see intermediate steps between evaluating a policy and updating a policy over greedy policy improvement steps. And through these iterations over the value function and the policy, we will actually end up in optimal policy and value function. How do we actually do this? You might have seen the Bellman expectation equation and Bellman operators in the previous videos, and we will also use them in here. So as a second solver to actually get optimal controllers for given known MDPs is policy iteration. And basically what we do is, this is a little bit formal what I just said, we always keep on applying the Bellman expectation equation in here to actually estimate a value function for a given policy, which is something that you could also do with matrix inversion, but you can also apply an iterative procedure in here. I will say a few words about this as well. And then you improve the policy by just acting greedy over the value function. Acting greedy over the value function, what does this mean? This is something we also have seen in the value iteration algorithm. So in the value iteration algorithm, we just kept on iterating over the value function until the value function was stable. And then we just extracted a greedy policy from that, and this policy was optimal. In this case, so in value iteration, we directly worked on the state values. In here, we calculate the state values always depending on the policy, but the greedy policy improvement step is just the same. So we just say that our policy pi prime This is always some of a notation you will always see. So this is an update on the previous policy. It's just the action that maximizes our Bellman expansion equation. This is actually the policy improvement step. Okay, so a little example from that, maybe then it becomes clear. So depending on if you're actually in an, so this is what you see here so this is your current value function in here. We have different states, so state D, E, F, G, and H. And what you actually see if you calculate the value of D, if you have a probability in here that you go from this, so let me see in here. So what you would see is in here. So if you have these are the successor states, and there is certain probabilities assigned, taking an action A and then ending up in these states, or taking an action B and ending up in these states. And what you will then see is if you take action B under your policy pi, you will get a reward of 6. Under your value function, you would get a reward of 6. And in this case, you would get a reward of 6.3, which basically means that now your policy, depending on this value function, would suggest to take action A in state D because it maximizes your state value. Okay, also the same procedure as in value iteration. Let's just talk about it a little bit through the pseudocode. I also told you a little bit about the intuition, and it's really similar to also what you have seen before. So in the beginning, we will initialize our value function and policy. Like, could be anything. So if you have any knowledge about your MDP, you could also add like prior knowledge on that, but you could also just arbitrarily initialize it. So then the first step is that we go, remember we have these two arrows, and the first thing that we do is we want to evaluate our policy pi, which is initially random or something, and we want to estimate a value function for this. And how do we do this? So this is really similar to what you have known or what you have seen in value iteration. So you have an outer loop that will run until you just go below some threshold, which is basically the accuracy that you want to get. I will say a few things about this because actually it's not necessarily, it's not always, as you also have seen in value iteration, it is not necessary to actually come to the real optimal value function to improve your policy. This is something that you also have seen in value iteration. So the policy converged much earlier than the value function. So you need to run, so you can set a larger threshold in here. Okay, so you have an outer loop that goes until some threshold. And then you loop over the inner loops, over the inner values, and this update or this estimation function is really similar to what you did in value iteration, but in contrast to value iteration where you applied the Bellman optimality equation, you just applied the Bellman expectation equation. So you want to estimate the value that you can get if you follow your policy pi that is given, and this means that you apply the Bellman expectation. So what can you expect from an MDP if you do act according to your policy pi? So this is in here. So you run this, and this actually evaluates your policy. It returns a value function that describes how much you can get from each of the states if you're acting to your policy pi. And then you can take the down step in your generalized policy improvement method, where you say, okay, I want to improve my policy. I'm just having a counter here, policy stable, which is true. It's just an indicator if I changed anything in my policy. So my policy was a mapping from states to actions, and I want to know if anything changes or not. And what I'm doing is I just consider each of the states, and I look at the old action that was assigned in my policy, and then I will apply the argmax greedy improvement operator in here. And if the old action is different from the new action, then the policy changed, and if the action was the same, then the policy is still stable. If the policy is stable, so there's no change anymore, then we can stop, and then we can return an approximation of the optimal value function and also the optimal policy. And if we changed things in the policy, we have changed the policy, so our value function estimate was wrong, so we need to re-evaluate our policy, get a new value function, and based on this value function, keep on updating our policy over the policy improvement step. Okay, so yeah, so actually how would that work? We have a small example. This example is also borrowed from Sutton and Bartow, so you can also go through the book in here. So actually, let's just say, let's just get an intuition of how policy evaluation actually works. So this is a simple MDP. It's also a grid world. You have these terminal states in here. You can start everywhere in the environment. It doesn't matter at this point. And you can take 4 actions, again, up, down, left, right. You get an immediate reward of -1 on all transitions, so just a movement cost or for transitioning between states. To simplify things, we assume an undiscounted episodic Markov decision process, so episodes end when we are here. We have no discount factor. Actions actually in here that would lead us out of the grid will leave the state unchanged. We had this also in the other examples before. And we initially assume that we start with a random policy, meaning that in any state, every action is equally likely. So like the initialization step is like uniform initialization. Okay. So what you see on the left side is here the iteration counter. So this is what we start. We actually initialize our policy, the random policy, and we initialize our value function, meaning that we do everything to 0. And what I'm putting on the right side is the greedy policy with respect to our current value function estimation also. So this is currently the initialization of our policy. And this would be the greedy policy that we would extract from the policy evaluation step. But still, the policy evaluation that we do now in the example is always with respect to the random policy. We do not really do the policy improvement step. This is just the greedy policy that we would extract from our value function. Okay, so if we have this, so this is our initial this is our initial value function initialized, and we have this policy. Just let's run policy evaluation. This is like very similar to what we did in value iteration, and you see a lot of similar things in here too. So we change the so we get a reward in here, so we get a reward for every step, but in the terminal steps we will end the episode and there will not be a negative reward. So this is the only states that we get a 0, and in all the other states we have a -1, of course. If we now at this point would extract a greedy policy from this already, we would already have an indication what to do better in here. So in this case, we now already would know a better thing to do than just acting randomly. Okay, if we keep on doing things, we will keep on updating the values. This is also the same that you saw from the value iteration. As we get more information for the successor or alongside states, we can also update our knowledge from our current states. So this would be the second iteration. And also in here, the policy really changes a lot more. So we get a more and more information of being better than just acting randomly. So if we go on, we can go and follow this along. After the third episode in here, we are far away from the random policy. So there is not any states where we have more than 2 states being selected. And if we just go on, value function, the value function would change, but actually the policy would not. So meaning that depending on your value function over policy evaluation, the greedy policy improvement would already lead to the same result even after the third iteration in this case, meaning that you do not, this is what I said in the beginning, so you do not need to really converge to a value function in here. It wouldn't change your policy that much. So what you see in here, going from the 10th iteration to like infinity, this is something where you will approximate to, will not change that much. So it will change the value function, but the policy is still the same. So you would just go to the third step, to the policy improvement, improve your policy, and then run policy evaluation again. So you do not need to run until numerical convergence at this point. Okay, so what do we see here? the main takeaway from this is iterative policy evaluation converges to VPy. So although you could also like numerically solve or analytically solve this via a matrix inversion on the linear system of equations, it's really much better in practice to just do the iterations on it. In this case, with 3 iterations and a few additions and multiplications, you're done. You can improve your policy. So policy evaluation eventually would converge to VPy. And the converge greedy policy is also guaranteed to be an improvement over the random policy. This is something we have intuitively seen in here. There's also a proof or hints to a proof that I will suggest in the following slides. And in this case, this is something that we really see very commonly in practice. Any greedy policy that come after, in this case, the 3rd iteration, are optimal policies. So just run policy evaluation for a few steps and update your policy and go on over again. In practice, this is a much better approach than running policy evaluation until the end. Okay, so the question, so with this procedure of iterating between the policy evaluation and the policy improvement step, the question is, why does this work anyway? So how can you see that if you evaluate a random policy and then keep on updating your policy based on the value function for that random policy, how does this actually improve? And this will not be part of any exam or something like this, but it's just being some intuition of the proof behind this. So why does general policy iteration work? Because we actually also build on top of that in the upcoming lectures. So to give you some intuition of the proof, just consider the following question: is the policy improvement making pi better? Pi prime better than pi? That's the basic question. So why should our policy improvement over these iterations would result in a better policy? And the question is, assume that for some state in your state space, in this case S, the action that you would select through pi prime is different from the action that you would select through pi. So actually your policy changes. And now the question is, should we use the new policy? And is this policy better or worse than the older policy? And the next question that comes to your mind is basically, how good is it to choose the action A in S and then keep on following your original policy pi? Okay? So you would actually select an action A that you would not select under pi, but in this specific time step, you select this action that is not proposed by pi star, but then keep on following pi. Okay? Not pi star, pi S. Okay, so just in this single time step, select A that would not be proposed by pi S, but only by pi prime S. And but afterwards keep on following the old policy. And this would basically mean, so if you also consider the Q functions, again also in the beginning, the question is the Q function of, so the state value function following policy pi, so the old policy, given S and A, where A is the action proposed by the new policy, is this Q function, which usually should be equal to the value function of the state A, is this Q value higher than the state value of the state under policy pi? If this is really the case, so if Q of pi S and A, but A would not be what pi proposed, is higher than the state value under pi of S, then we would expect that using A is always a better thing to do when we are in state S, right? So if we encounter S again, it would again be better to select A. And that would then in turn also mean that the new policy is better, right? So if this is the only situation where the two policies are different, and there's one time step in which it was better to do this, then we would expect policy A to be the policy pi prime to be better than policy pi. So this is the intuition. So we just formulated like an equation in here that we can follow along. So in general, let pi and pi prime be any pair of deterministic policies. such that for all of the states we have in our state space, the value of q pi under s pi prime, so actually the action that the new policy would provide under is higher than the value of our state. So if we would have pi as not pi prime here, but only pi, this would be equal for everything because the q value is the max of the v. So if this is larger or equally or larger than v, this means that pi prime must be as good or even better than pi, which basically means that also the v function should be larger than this or equal, so equal or larger. And again, consider now the special case that exactly for one state the selected action is different, which is actually part of the non-strict inequality formulations above. Okay, so this still holds even if it's only for one state. And then you can follow along. So if q pi SA is really bigger than q pi, than v pi of s, then you can follow along and say, okay, I roll out the expectation of our trajectory, and this is just an intuition. You can look at it afterwards. So what you basically do is that you roll out your episode and you formulate it and you reformulate v over q, and then you see that in the end this is satisfied, indeed satisfied, and yes, and note a strict inequality above leads also to a strict inequality below. So this is just an intuition. Read over it. I think it's really getting along. But this is basically the proof why general policy iteration is really proven to be an improvement. Okay, so actually I will not go over the slides again. I will just have them. I just compiled them through the literature. You can look at them. They are not part of any exam, so it's just to give you more intuition about why general policy improvement really works and why it's a nice framework that you can also use in practice and that we will use a lot in practice. Okay, so now this was our second algorithm for actually finding optimal controllers for given known MDPs. The algorithm is called policy iteration, in contrast to value iteration, where we directly work on the state values. Policy iteration keeps an explicit representation of the policy, so we keep on updating we keep on estimating a value function for a given policy, then update the policy, and if we updated the policy, then we re-evaluate our value function and keep on over again until we converge to the final policy, to the final optimal policy and optimal value function. Two final remarks for that. So in the example before, we considered deterministic policies at points. So in the example we did, but also in the math, we also considered probabilistic policies. In this case, everything can be extended to this. I also talked about this. Do we need to evaluate upon convergence? No, we do not. And this is also like the biggest advantage of policy iteration. We do not need to run everything until something converges. We can just go on and take over the next steps. And like the extreme case would just be to say, let's do one policy improvement and let's do one policy evaluation. And if we do this really you can think it through. It really breaks down it in the essence to value iteration. So actually these algorithms are really closely connected, but if you like doing the policy evaluation step and then also the improvement step like in between, this somehow collapses to the same algorithm, although being a little bit different in detail. Okay. Yeah, so also in here there's a nice example from Andrei Karpathy that you can use to play around with it a little bit. I will show you the thing on the in here. You see it is familiar because it's actually the same web page. You have the same MDP. You can change it and play around with it as well. And then, whereas we did the value iteration in the example before, you see it in here, you can just stop it and reset it. What you can also do is like having an initial random policy. So you see the arrows in here, it's not completely random. It's like initialize a little, okay, because you do not go to the left. So it's a random policy in the end. And what you can do is like, you can run policy evaluation on it. So you can run policy evaluation, a few steps, then you can update your policy evaluation, policy update. And if you keep on doing this, can go on. Also, policy update is only worth it once, because we would do the same thing again. And you can like go on, and update your policy, and you will see like how the state space actually converges a little bit. And yeah, so this is because this is also really easy, because my policy evaluation is just one sweep, like really quickly, and the update is also just one setting of parameters. And you see now, through a little bit of clicking, I solved the whole MDP within less than 1 minute. So play around with this. You can also like change a little bit the values, and I think it's a very nice example to give you more intuition about policy iteration. Okay.